Welcome to lecture 19. In this lecture, I continue the derivation of the Einstein Field Equations. We now know three rank 2 tensors that are covariantly conserved. These are the energy momentum tensor, the metric tensor, and the combination of these tensors that we derived in the last lecture, where these tensors are here are just some combination that involve the derivative of the metric tensor. Since we can use effective field theory arguments saying that up to two derivatives, these are the only rank 2 tensors that we can build. These three combinations or these three tensors are the only rank 2 tensors that have the property that they vanish under action of the covariant derivative. Let us now study the consequence of having these three tensors that have this property that they are covariantly conserved. It turns out we can use the three conservation laws, equation 19.1, and we can combine them into a single conservation law by just using linear combinations of the three. To keep things as simple as possible, I will choose one coefficient of these three to be unity, and then we have two arbitrary coefficients that we can use to build linear combinations. If I choose the name of two constants being lambda and C2, then the form of the conservation law that we get is that I chose unity for the first constant that multiplies this conservation law involving the tensors R. Then for the metric tensor, I chose the conservation coefficient to be lambda, and for the energy momentum tensor, I chose the constant to be minus C2, where the minus sign is convention and will become clear later on. Let's now look at solutions to this conservation law 19.2. Arguably, the simplest way to satisfy this conservation law is if the term in parentheses itself is vanishing. So basically, it's saying that the derivative of something is zero if the something in the parenthesis itself is vanishing, because then the derivative of something that's zero gives back zero. So let's explore this possibility. If this is the case, then we find that the following relation has to be true for these two tensors. So we have, on the one hand, this combination of tensors equal to the energy momentum tensor here. And we can now proceed to study the properties of this particular requirement, which again, as a reminder, is one particular solution of the conservation law that we derived in equation 19.2. So we have derived the conservation law from the Beyontic identity in an earlier lecture. I just wanted to give some names for the symbols appearing in these equations. To get started, the R that appears in these equations will be called the Ricci scalar. It's a scalar because it has no indices, and indeed that will also be the property of this quantity R. Next, the tensor that has two indices, mu and nu, will be known as a Ricci tensor because it's a rank 2 tensor having two indices. We got both of these quantities from contractions of this tensor R, rho, mu, nu, lambda, which was the combination of the two covariant derivatives that were acting on a vector in the last lecture. And this rank 4 tensor we will refer to as the so-called Riemann tensor. So summarizing, starting with the Riemann tensor, we can do a particular contraction to get the Ricci tensor, and if we do another contraction, we get the Ricci scalar. So everything follows from the properties of this Riemann tensor, which, as a reminder, is composed of two derivatives of the Christoffels plus two terms that involve Christoffel symbols squared. Note that the name tensors and scalars is not just an arbitrary name for these. These are actual tensors and scalars under general coordinate transformations. Okay, let's now go back to our equation that we got from the conservation law. The conservation law 1943 has many independent components. To get started, we can look at the trace of these equations. To make it a little more interesting, let's look at the trace of this equation for an arbitrary number of space-time dimensions, which are called d. So in particular, our universe in 3 plus 1 dimension would have d is 4. If we look at the trace, then we'll have quantities such as the trace of the Ricci tensor, the Ricci scalar appearing, and we will have the trace of the metric tensor, which is just the number of space-time dimensions d. So if we do this, our equation that we get is r minus d over 2r plus d times lambda equals to c2 times the trace of the energy momentum tensor. We can solve this equation for r, so we get that r is equal to d times lambda minus c2 times the trace of the energy momentum tensor divided by d over 2 minus 1, which in particular in 4 dimensions just leads to r is 4 lambda minus c2 trace of the energy momentum tensor. It also tells us that if we are in 2 dimensions, because we have d over 2 minus 1 in the denominator here, there will be a problem with our field equations 19. So the trace of the field equations 19.3 involve the energy momentum tensor and the Ricci scalar. For any manifold, we sort of talked about how the Ricci scalar is defined in terms of the Riemann tensor, and the Riemann tensor is defined in terms of derivatives of the metric tensor. So long story short, once we have the metric tensor, we can calculate derivatives of it, and we hence can get the Ricci scalar for this particular manifold, such as manifolds we have previously encountered in this lecture. Since I'm lazy, I will do part of this calculation of the Ricci scalar using symbolic manipulation programs, the way that I've introduced them before in the present lecture. And this has the simple meaning that calculating the Ricci scalar typically is very tedious. So this is a clear task where it would be useful to employ computer-assisted calculations. Let's start with Euclidean coordinates, where we can still do everything if you want so without computers. Euclidean coordinates in Rn, an n-dimensional Euclidean manifold. In this case, the metric is just a diagonal tensor with just ones in the diagonal and nothing else. Since the Ricci tensor is defined based on derivatives of g mu nu, the derivatives of constants is always vanishing. So clearly, we must get that the Ricci scalar is identically vanishing for the n-dimensional Euclidean space. So that was easy. Now let's do something a little bit more tricky. Let's continue with R3, but instead of using Euclidean coordinates, let's do a non-trivial example where we use spherical coordinates. So our vectors x, y, and z are defined in terms of the spherical coordinates r, theta, and phi. We have already discussed these coordinates, and we have said that if we want to express the coordinates or the metric tensor in terms of the new coordinates r, theta, and phi, the metric in the new coordinates is again a diagonal matrix with 1 r squared and r squared sine squared theta in the diagonal. So now we have a metric tensor that depends on the coordinates. So derivatives of this will not be vanishing. So let's see whether we can still calculate the Ricci scalar for this example. To do so, let us use the symbolic manipulation package. Again, I hope you can see this. So basically, I start by evaluating the code here, and then I want to use my coordinates r, theta, and phi as I have in my lecture. This is my metric, diagonal tensor, and it has the required form. So this is the metric tensor that I'm going to have. So I'm now going to say RG tensors metric coordinates. And if I do so, I'll get in particular my Christoffel symbols. So we can look at our Christoffel symbols, and indeed the Christoffel symbols have non-vanishing entries, so they're not all trivial. From the Christoffel symbols alone, it's kind of possible, but a little bit tedious to get to the Ricci scalar. However, the computer program also calculates the Riemann tensor with down, down, down indices. So this is Riemann for indices all down. In order to get the quantities we called the Riemann tensor in our lecture, we want to use a metric to pull up the first one of these indices. We can do this, and we already see that, okay, there's all zeros. So that means that whatever we do, we will find a Ricci scalar that is 0. But nevertheless, just to be complete, that is our Riemann tensor the way we have it. We can now get our Ricci tensor by sort of summing over the corresponding quantities. So we have to sum the first one, we'll leave the second one the same, and the third one. And we have to sum over all entries. See how I call this? I call this X chord. See if this is right. X chord. That's because I 3 coordinates from 1 to 3. We find that the Ricci tensor is vanishing, and then we can simply get the Ricci scalar as the metric tensor trace of the inverse metric tensor on the Ricci tensor, so we get 0 for the Ricci scalar. So what we find is that, if we go back to our example here, we find that the Ricci scalar for this space here is again 0. In some sense, that was to be expected, because we're still dealing with R3, and R, Ricci scalar, is supposed to be a scalar under coordinate transformations. So it shouldn't matter which coordinates we used. We showed that for Euclidean coordinates, it was trivially 0. So now we used spherical coordinates, but we haven't changed the manifold. So R0 has to be, if you want, the corresponding result. Now let's do something a little bit more interesting. Instead of R3, let's now look at the spherical surface. So that is sort of similar to the metric we had before, but we allow R no longer to vary. We just sort of take the surface of a sphere, and as such, the coordinates are the same. They are just theta and phi, but the metric tensor is now just given in terms of a diagonal matrix that has 1 and sine squared theta along the diagonal. So we can go back and calculate the corresponding properties for this particular tensor. So let's go back to our example where we want to look at the spherical surface instead of spherical coordinates. So we have 2 coordinates, and our metric is the following form. So now let's, what did I do? Spell px. So if I then use the symbolic manipulation program to sort of calculate properties of this space-time, then again, the Christoffels for this space-time or this manifold are again non-vanishing. But in this case, we can directly calculate the Ricci tensor. The program has done that for us. In particular, not only do we have a non-vanishing Riemann tensor, we also have a non-vanishing Ricci tensor, so you can see it here, and we have a non-vanishing Ricci scalar, which in this case is just 2 over R squared. Just to be consistent, let me just point out that indeed this Ricci scalar here is the same as before. So we have R u down, down, down is given by the following form here. And if we take the sum of this quantity with the first and the third index, then indeed that gives us back the Ricci scalar that we had before. So this method that I sort of used to calculate the Ricci scalar, if you want to by hand in the previous example, gives the same result for the case of the spherical surface. Okay, so going back to the slides of the lecture, we find that the Ricci scalar for the spherical surface is non-vanishing. It's given by 2 over r squared. And in particular, it is small for large radius, and it is large for small radius. And in particular, it's non-zero, unlike the case of the Euclidean space in n dimensions, which we discussed before. So what does that now mean? It means that for the Ricci scalar, we found that r is 0 for the manifold Rn, regardless of which coordinates we chose. So we chose Euclidean coordinates, we found r is 0. We chose spherical coordinates, r is 0. That is to be expected for an actual tensor that is independent of the coordinates that you actually choose. But the spherical surface gave us a non-vanishing result. The r was small if the radius of the sphere was large, and the r was large if the radius of the sphere was small. So basically, the interpretation will be that r will be sensitive to the local curvature of the manifold. So if you have a very, very large spherical surface, then as r becomes almost infinity, that surface becomes almost flat. So r goes to 0, like a flat manifold, like Rn before. But if r, the radius of the sphere, becomes very small, then the Ricci scalar becomes larger and larger because you're going to the direction where your spherical extent is very, very small, and the curvature becomes larger and larger. And that concludes the present lecture, and we'll try to find more results from these field equations that we talked about in the next lecture.